Today, I will tell you something about the photometric monitoring of exoplanet host stars. And just in the second half of the short talk, I will tell you about the fraction of variable host stars, because the first one I will use for presenting our survey of photometric monitoring. And the photometric monitoring here is an example of how it looks like when we monitored a variable host star. This is GJ1214 over several years with a 1 meter class telescope. This is used to learn something about the star spots on, or the first of all, the activity itself of the host star, and second also a little bit about the star spot properties. Because in the talk so far by Brett and Giovanni, you heard about deriving the properties from occultations, but you do not know in advance if you will get occultations in your transit observations, and therefore these simultaneous observations, the simultaneous monitoring, were planned ahead, and they tried to cover actually the period of the transit observation, the spectroscopic transit observations that you did for transmission spectroscopy. We did this over several years for several teams, that several people asked for complementary observations. And in total, we observed over the last years 44 targets with 3 robotic systems, all 1 meter class telescopes. And here you see the targets in green, over in black all the planets known so far from the TAPCAT catalog. And on the y-axis, you see their potential transmission spectrum. The potential transmission signal for 1 atmospheric scale height. So most of the targets were actually among these ones that we are interested in for doing transmission spectroscopy, because they have these inflated atmospheres and large potential signals. Here you see some examples of how these observations, these ground-based observations, look like for 1 observing season. So per observing season, we observed these for, let's say, 4 months on this order in multiple colors. Here you see for these targets the colors B and R, so very blue and pretty red. And you see here examples from quiet stars to pretty active ones, and the majority of targets end up to be quiet, at least to our precision that we achieved. But this is also what you would expect from the statistics derived from the Kepler telescope, how active solar-like stars actually are. And for most of these targets, when they were included in the papers, these complementary data were often simply used to say, we do not measure the activity, so therefore we think it is likely that the effect is negligible, the effect of the activity on the transmission spectrum, or it was also included in I think in 2 TGV studies, because also for transit timing variation, these active regions might have an influence. But the majority of stars have been quiet, and therefore it was just used with this simple statement. But for example, here I already mentioned these pretty active M-dwarf GJ1214, where we had actually even observations of 3 different colors. And what was possible to actually derive for them? We applied here in the paper from 2018, we applied here the light curve inversion to a star sim. And in the subsequent talk by Ignazi, you will hear more about this tool, I think. And then the quantities we actually derived were the filling factor, spot temperature, active latitudes, and also the lifetime over spots, because we had these measurements over 5 years. And that was a spot map here with time on the y-axis and longitude on the x-axis, and you saw these active longitudes which remained to be covered over the length of the duration, over the length of the observation. Interestingly, there was also this transmission spectroscopy work of Ben and Nestor, the 2 chairs of our SAC 21, and they derived in their transmission spectroscopy work, they derived this positive slope in the optical transmission spectrum. We know that the planetary transmission spectrum is rather flat. So in this case, it was possible to say that, or they came up with the likely explanation that bright regions, actually unocculted bright regions, caused this effect of this positive slope. But this is something that was pretty interesting when we looked at our light curve, at our monitoring light curve, because the three transits they are marked here with these dashed lines, and you see that they all happened at rather dark time of the host star, and our light curve inversion tool actually did not give any indications for faculae, but we derived the temperature, the spot temperature, always to be positive. That meant in the case of our StarSim tool that this is dark spots, and we had actually the feeling that this is actually dark spot dominated the host star at the time of the transits, and that showed to us that there's something we still don't understand, that there's a problem, because between these two observations, actually we take this monitoring in the hope that we can use it to know about the star spots and to correct the transmission spectrum. Here in this case, actually the two techniques actually told different stories, and yeah, in the end we just presented ideas how to explain it, because we haven't had any scientific proof. And the idea was that certainly it's not just unocculted regions, but also a mixture of unocculted and occulted regions. But in the end, that was just an idea, and presented actually showed that there's still problems. And unfortunately, though this work is now 3 years ago, I haven't seen many other examples like this of multicolor photometric monitoring and simultaneous transmission spectroscopy in the optical, where actually you could compare the results on the spot properties you get from these two different techniques. And therefore, I think there's a need for further tests of the spot correction method. And the suggested observation would actually be, in principle, to have it like for the case of GJ1214, that we have multi-epoch transmission spectroscopy plus simultaneous multicolor photometric monitoring, at best from an active star, but with a planet with a very thin atmosphere, because in this moment we just want to learn about the spot correction and not have the slope in the transmission spectrum also degenerate with features of the planet atmosphere actually. And an example for such exercise would be HATP20. And yeah, this is just a suggestion, because I actually still have the feeling that that it is not clear exactly how to use the one method to correct the other. Okay, and then just how many stars are actually variable? How much do we need to wonder about this? It is, I wanted to use the observations that we actually have for the hot Jupiter host stars and not extrapolate from Kepler. And therefore I searched the literature. I searched the discovery papers of all the ground-based hot Jupiter host stars. That was actually a crazy endeavor that had something to do with Corona times and being home with the kids, doing homeschooling with them. And I found actually in many of the discovery papers information on the stellar variability. It is periodic stellar variability that the people looked for. So it is not variability by itself, but periodic variability. 200 were non-variable, but for 60, I found the information that they are variable. And for 25, they have a peak-to-peak amplitude of more than 1%. So this is, of course, that's just my gut feeling from the last years, that we start to be worried if the star is variable by more than 1%. With future observations, of course, that will be that then this might be, we might also need to take care about less variable stars. So here, therefore, here on the last slide here, 25% of the host stars we already know from existent observations, information given in the literature that they are variable, and 10% of the host stars show variability greater than 1%. Yeah.
Thank you.
Thank you
so much. So there is one question in the Slido about that. Could it be that the planet went through a dark band of spots which emulated a facula-dominated interpretation?
Can you repeat it again, please?
That the planet went through a dark band of spots,
yeah,
that mimic the facula-dominated feature that we see. So we don't see the spot occultation because
that we do not see. Yeah, actually, this is also what Ben and I then discussed by email, because he emphasized that he does not see any spot occultations, and that was my only idea how to get these two observations, the monitoring of the host star and their result from the transmission spectroscopy, in line. I said certainly, or maybe you might have some occultations there, and he correctly said, yeah, but I do not see them. And therefore, in the end, it was just ideas what it is. The observations were not precise enough to actually, to solve this issue on GJ 1214 back then.
Okay, I have also a question. The facula contrast ratio is smaller, so what's the needed precision to detect and also measure the temperature contrast or the filling factor? Is it possible with the stellar photometry to get the parameters of facula?
I would like, I think I can forward this question to Ignacy, because he might tell more now on the StarSim tool, because that was work done by the guys from Barcelona, Ignacy and Kike Herrero, that they modeled the light curves.
Yeah, I can actually answer right away. We just fix the temperature to a solar value, and then we determine the facula to spot ratio. That's what we do. Actually, we don't determine the facula contrast ratio. Yeah.
Okay. Also, there is another question. How long of the baseline do you need to establish the photometric baseline of the star? And could this affect the bright cold spot interpretation? So how long should be the baseline photometry to get some information?
Of course, what we want to have is at least 2 to 3 rotation cycles. So that depends then on the rotation, on the time scale of variability, which is the stellar rotation period. Yeah.
Okay. Thank you.